Hi, I'm Eric. I work at Le Bon Coin in Paris. I'm a developer. And today we'd like to talk about Plankalkül, a really ancient programming language. Some of you might have seen a presentation at Newcraft a couple of years ago by Laurent Bossavit called Perpetual Infancy, Why Software Doesn't Seem to Be Growing Up. And you might got interested in the history of programming languages. I did. Right, so what was the earliest programmable computer? What was the earliest programming language? For the programmable computer, we already have a reasonable idea. You have probably heard of the ENIAC, designed in the US and completed in 1945. You have probably heard of the Colossus in the UK in 1944, all designed for helping in the war efforts. Less well known is the Z3, the computer from Germany, designed completed in 1941. It was programmable using punch celluloid tape, not punch cards, the same kind of film you have in cameras. It was designed by a person called Konrad Zuse. Konrad Zuse was a design engineer in an aircraft factory before the war, and that required him to perform lots of routine calculations by hand. So starting from 1936, he started to design computers, and he designed three important computers between 1936 and 1945, using basically the same general computing principles. This person actually founded a company in the middle of the Second World War. He founded another company after the war, using funding from a university in Switzerland and IBM. In 1967, his company had built more than 250 computers, and at that time, it was acquired by Siemens. Right, so he designed the Z1 computer completed the Z1 computer in 1938 in his parents' living room. That's a picture of his parents' living room. And then he moved to the Z2, which he completed in 1940. That one took several rooms in his parents' apartment. The Z1 was a purely mechanical computer, very unreliable. It was programmable from what I understand, but not Turing complete. One of the reasons why it's not considered one of the earliest computers. The Z2 replaced some of the components with electrical relay circuits, making it much more reliable. And from that, he got funding to work on the Z3. The Z3 was completed in 1941. The celluloid tape thing is here. That's the thing where you actually put the holes in the celluloid tape to give your instructions. It was later demonstrated to be Turing complete. When I say later, I actually mean the end of the 20th century. And in 1942, he started to work on the Z4. The Z4 was a completely different design. However, in 1943 and 1945, early 1945, his computers, the Z1, the Z2, and the Z3 were destroyed by Allied bombings in Berlin, and also much of the blueprints. So in 1945, he had to stop working on the Z4 because he had lost much of his workshop, and actually there were no parts he could get at the time because of privations during and after the war. So in 1945, Zuse switched back to theoretical studies, and while he was working on the Z4, he had already started to realize that programming in machine code was not much fun. And in 1945, he decided that it was time to give it a good go. So he completed a manuscript in 1945, but he didn't get to publish it. Only in 1948, he published excerpts in the Archiv der Mathematik, and also introduced his language during the annual meeting of the Gesellschaft für angewandte Mathematik und Mechanik, the Society for Applied Mathematics and Mechanics. There were almost no reaction to his publications. Plankalkül. Plankalkül means formal system for planning. It is a sign that Zuse was strongly influenced by David Hilbert, a German mathematician who actually had introduced very similar names for his own formal systems. He's basically the person who designed modern formal systems. In Plankalkül, you have ration plans. A ration plan is what we could call today a program. A ration plan is made of subplans. Subplans can be made of other subplans. And results can be sent back to the first original main plan. He did not, however, anticipate recursion. Here is an example of how you would write something in Plankalkül. And the fun part is the two-dimensional notation. This is basically the signature of a plan. It says that plan 1.1 takes one value as in input, V0, and one value as output, R0. The R with the parents, R parents V, mean Randauszug, that is border summary. Well, I don't know how to say it any differently, but it's a signature of a function. In a program, you have those funny lines. The V line, the K line, the S line. The V line is the variable, no, with a German accent will be better, variable index. That's where you specify which of the input variable, which of the output variable you're interested in. Here we have a single input variable, V0, so the index is 0, and you might have any number of them. Funnily enough, in his paper, Konrad Zuse muses that, well, there aren't enough letters in the Greek alphabet and in the German alphabet to cover all the possible situations in a program, well, in a plan. The K line is the componenten index, that for subparts of variables. It turns out that variables can have subparts. We might refer to them as records nowadays. And you would specify which subpart you might be interested in by putting a number in the K line. Then we have the S line. The S is for structure, that is data type. Structure 10 is an integer. It turns out that there's different notation for that. Maybe an A, I'm not quite sure why. A seems to be for advanced data types. From what I understand in this paper, they are pretty much replaceable. So yeah, it is a bit verbose, as you can tell. It turns out that in this paper, Konrad Zuse talks about the explicit form. This is the explicit form, but it was so painful to write that he will actually use in an implicit form, something much shorter. Variables. So we have the V variables, that's the input values, the R variables for results. The Z variables, the switch inverter, are the intermediate values. Their scope is only within a plan. We also have constants. I've never seen them used in this paper, but must have seemed like a good idea. Data types. We have a very important data type, and that's the bit. You need to realize that at this point, people were still designing analog computers, and some others were designing computers with decimal values, not binary values. But he was very clear in his mind. He was not the only one, but at least he made it very formal that the bit was something super important in programming. So a bit here is called the structure 0 or the S0. He called that the YANA inverter, that is a yes-no value, and everything can be built on top of that. So we have various other types, arrays of any number of bits, tuples, any number of bits, and then we have types that he added as, I would guess, syntactic sugar that represent the normal type that you would work with, including complex numbers. Operators, so the most important one, the simplest one, is the assignment, the double arrow. This assigns value 0 to the result value 0, the first result value, which is an integer, 10 integer, got it? Easy enough. We have conditional execution. So it doesn't really talk about Boolean values in this paper, although you could say that they were there. But it does talk about conditional execution. He has a special symbol for that, the arrow with a dot below it. So this means that if V0 is greater or equal to 1, then we execute what is on the right. That is, we assign value V0 to the result value. So that's predicates for you. Loops. Loops are Wiederholungsplans with a W, as you would have guessed. A Wiederholungsplan is something made of statements, one below the other. Each statement have a predicate on the left, the arrow with the dot below it, and a further plan or further piece of program on the right. So this loop here is identified with a W. Then you would go through the first line first, trying to evaluate the F predicate. If the F predicate is true, then you would execute P. If the F predicate, yeah, right. So one thing you need to remember is that there's nothing protecting you within a loop, and you need to remember to have an exit clause. The exit clause is the F with an horizontal bar on top of it, like the notation you would have in mathematics. Actually, his paper is infused with mathematical concepts everywhere. It's actually making it pretty hard to read. So to be able to remember, to be able to exit your loop, you need to invert the predicate you had so that you would be sure you'll be able to exit the loop. And the special keyword for exiting a loop is fin, which is not the French word for n. It is actually coming from Latin. Turns out it's the same word. All right, so, and you would have any number of them, right? Not just one, except that you would have to evaluate them all the time. As you can see, he was quite liberal with adding special notations like the large square brackets here. That also makes this paper a bit hard to read, but you need to understand that at the time he was doing it all on paper. So he added a bit more syntactic triggers for loops. A simple loop is the W0, which would go n times through the following piece of plan. In this example below, we start by assigning 1 to the intermediate value Z0. Then W0 expresses that we're going to loop V1 time through the square brackets immediately on the right. And every time we're going to multiply Z0 by V0 and assign the result to Z0. And finally, when we're done with that, then we're going to assign the result, the end result, to the R0 value. Essentially, this computes the power of a value. We're computing V0 to the power of V1. We're multiplying V0 by itself V1 time. Okay, here is another example, straight from the mouth of the horse. This is part of a program, a chess program he wrote. He actually did write a chess program like everybody was doing at the time, like Turing did, apparently. This computes whether two squares in the chessboard are adjacent. It compares V0 and V1. So, sorry, two squares are adjacent if they are different. V0 must be different from V1. If the subcomponent 0, I guess the row, the difference in the subcomponent zeros are equals or less than 1. Turns out that L is an alternative notation for the bit of value 1. And the subcomponent 1, that is probably the column, must not differ by more than 1 either. The equivalent of that is pretty much this, must be different. The absolute values must be equals or less than 1, and for both the rows and the column, and that checks whether they're adjacent. I could go through a few examples, but it turns out that it gets really verbose really quickly, and that's just a very, very simple example compared to the rest that you can find. So, Plankalkül, most of you probably haven't heard of it, and for a good reason. It seems to have had some influence on the Plan language designed by this person, Heinz Rütishauser, Swiss mathematician. He designed that language in 1949 and completed it, I think, in 1951. It turns out that this person was actually one of the architects of the Algol language. Much later, it did acknowledge that Plankalkül had an influence on him, a strong enough influence that the name superplan is actually coming from the ration plan in Plankalkül. However, the syntax itself is pretty much not visible at all in Algol, except maybe the way some variables are initialized. And Tuzer was quite bitter by the end of his life to see that one of his life achievements were not acknowledged by other members of the community. So, in this little talk, I wanted to show that looking in history is really interesting. You find stuff that existed much earlier than you expected. Actually, it was so early that it did not anticipate compilers at all. And you can tell because in this paper, there's no way to easily compile this code. The people who did write a compiler eventually in year 2000 had to go through a whole kind of hoops to be able to tweak the language into something that was possible in a text file. And they didn't even implement the whole of it. Two-dimensional notations. I mean, how crazy is that? I mean, we cannot even get our brains to have these sort of ideas nowadays. I've never seen anything any remotely close to that in our modern computing languages. And still, for him, it just, well, I don't know. He didn't really know how to refer to values in an array, so why not have an additional line? Still, it was quite modern. I did not even go through all the list manipulation stuff he talked about. In some ways, his language is close to functional programming. In other ways, it's actually an imperative language. It was designed in Germany. When I started looking into this, I was pretty sure that the Americans and the British were the only ones competent enough to design computers. And still, in Germany, someone managed to reinvent the whole thing by himself in his apartment. By the end of the war, he did have a team of 2,000 people working with him, but it was all his idea. Some stuff are in German. I mean, again, we can't imagine that nowadays. Some stuff are even in Latin. So there are many more things to discover in our history. I hope I'll spend a bit more time working on that. I hope you will too. And maybe next year, some of you will give more presentations on more languages. Thank you very much. We have a few minutes for questions, if you have any.
Did you hear of SUSE before learning about his language?
I think I had.
I was aware of that. I was already knowing that, but I was not knowing about the language. I never read about the language.
I think I had heard of it in passing. I didn't really realize who he was. So SUSE was a bit ignored for most of his life. I mean, he was his computer had been actually acquired by universities and some companies in Germany, but outside of Germany it was total unknown. There's been a revival of interest in him starting in the 80s. Actually, Donald Knuth even wrote a paper that mentioned Plankalkül in 1976, I believe. And there have been quite a few papers written since then. So I guess some of them have been referred to some in other things I've been reading, but I didn't realize the significance of the thing. The Z3 is really surprisingly advanced compared to the ENIAC, for example, which for a long time was considered the only really early programming computer. So yeah, I heard of him, but I didn't really realize who he was and what he had been doing. All good? Thank you very much.
I have another question.
Oh, sorry.
Sorry. Did you find any trace of lambda calculus in the Plankalkül language?
I don't think I went into details enough to answer that. I would say probably, I don't think there are many traces, no. It's considered more an imperative language than a functional language for sure, even though there are some aspects. But probably not lambda calculus, no.
So he has basic types.
Yeah.
Not everything is coming from 1 and 0 or just applying.
Oh. I'm not sure how to answer that. Sorry, say again?
Function application is not the paradigm.
No, I don't think it is, no. Thank you.